Have you ever stopped to think about how the trillions of cells in your body actually stay alive? I mean, really, think about it. Every single one is like its own tiny, complex city. And just like any city, it's got to have borders, right? It needs to control what comes in and what goes out. So today, let's dive into the incredible world of cellular transport.
And that's really the central question, isn't it? Every cell is wrapped in a membrane. Think of it like a super sophisticated border crossing that separates the inside world from the outside chaos. Getting things across that border, nutrients in, waste out, is literally a matter of life and death. And our cells have some absolutely brilliant strategies for managing all that traffic.
When you boil it all down, there are really two main game plans. First, you've got passive transport. This is like floating down a river. You just go with the flow from high concentration to low. It requires absolutely no energy from the cell. Then you've got active transport. This is the complete opposite. It's like swimming upstream against the current. It costs energy, but sometimes you gotta do it to get things where they need to go.
All right, first up, let's talk about passive transport. This is the cell being incredibly efficient. It's basically letting the fundamental laws of physics do all the heavy lifting, so it doesn't have to spend any of its own precious energy. Now, the simplest form of passive transport is something called diffusion. It's just a natural tendency for things to spread out. Think about the smell of coffee brewing in the kitchen. Those aroma particles don't need a push. They just naturally move from where they're super concentrated, the coffee pot, to where they're less concentrated, filling the whole house. That's diffusion.
And this is a perfect visual of that process. You drop some ink into water, and without anyone stirring it, the particles just start moving, bouncing around, and spreading out. They go from that one crowded spot until they're evenly mixed throughout the water. Simple as that.
But this spreading out doesn't always happen at the same speed. A few things can change the rate. For instance, higher concentration, higher temperature, or more pressure. All of that makes the particles zip around faster. And of course, the substance itself matters. Big, bulky molecules or particles with an electrical charge have a much tougher time squeezing through the cell's membrane.
So here's the cool part. Once everything is all spread out, the movement doesn't just stop. It hits a point called dynamic equilibrium. The molecules are still zipping around like crazy, but for every one that moves to the right, another one moves to the left. The end result? No overall change. It's a perfect moving balance.
Okay, but what about stuff that's too big, like glucose, or things that have an electrical charge, like ions? They can't just sneak through the membrane on their own. They need, well, a special doorway. This is where facilitated diffusion comes into play. It's still passive, so no energy is needed, but it does require a little help.
And those helpers are called transport proteins. They come in two main flavors. You've got channel proteins, which are basically just tiny tunnels that can open and close. They're perfect for letting small ions shoot through. Then you have carrier proteins, which are more like a revolving door. They grab a molecule, change their shape, and then release it on the other side. And you can see the two different styles right here. On the left, the channel protein is just an open gate. But look at the carrier protein on the right. It has to physically change its shape to shuttle that bigger molecule across. See? Two different methods, but the same outcome. Getting things across the membrane without burning any energy. Okay, now we need to talk about a very special, very important type of diffusion called osmosis. This one is so critical it gets its own name. Osmosis is all about one thing and one thing only: the movement of water. It's how water moves across a membrane to try and balance out the concentration of other stuff.
Take a look at this classic YouTube experiment. That membrane in the middle lets water pass through, but it blocks the bigger sugar molecules. So what happens? Water naturally flows from the left side, where it's more abundant, over to the right side to try and dilute the sugar. It's water's way of trying to make things equal on both sides.
And this has huge consequences for our cells. If a cell is in an isotonic solution, the water flow is balanced and everything's good. But put it in a hypotonic solution, where there's less stuff dissolved outside, and water will rush into the cell, maybe even causing it to burst. The opposite happens in a hypertonic solution. Water rushes out, and the cell shrivels up. So far, everything has been pretty easy, just going downhill with the flow. But what happens when a cell needs to pile up more of a substance inside than there is outside, or push something out that really wants to flow in? Well, that's when the cell has to roll up its sleeves and spend some energy on active transport. Yeah, this is the definition of pushing uphill. Active transport uses energy to physically pump substances from where there's less of them to where there's already a lot. To pull this off, it needs to pay up, using the cell's universal energy currency, a little molecule you might have heard of called ATP. And the most famous example of this is the sodium-potassium pump. This thing is a masterpiece of molecular engineering. It's in a constant cycle. It grabs 3 sodium ions from inside, uses ATP energy to change shape, and kicks them out. Then it grabs 2 potassium ions from outside and brings them in. This little pump is absolutely essential for your nerves to fire.
Cells can also be really smart about their energy budget. Check this out. In something called coupled transport, the cell uses the strong downhill rush of one substance, like sodium wanting to get in, to power the uphill movement of another substance, like sugar. It's like using a waterfall to power a mill that lifts something heavy. Super clever.
Okay, so we've covered small molecules and ions, but what about the really big stuff, like entire proteins or hormones? No channel or pump is going to handle that. For that kind of heavy lifting, cells have to turn to something called bulk transport. The way the cell does this is by wrapping the cargo up in a little bubble made from its own membrane. This bubble is called a vesicle. To bring things in, the cell membrane literally reaches out and engulfs the material. That's endocytosis, or you can think of it as cellular eating. To ship things out, a vesicle from inside moves to the edge, fuses with the membrane, and dumps its contents outside. That's exocytosis.
So let's just step back for a second and look at the whole master plan. We've got diffusion, osmosis, protein helpers, energy-burning pumps, and even bulk transport. What's the point of all this activity? It all comes down to one single crucial goal: maintaining balance.
And this table here is basically the ultimate cheat sheet. You can see that clear division, right? The passive methods up top need no energy. They just go with the flow. The active methods on the bottom, they require energy because they're fighting the flow or moving huge cargo. Every single method is a specialized tool for a very specific job.
And this quote, right here, just hits the nail on the head. All of this incredible work, the pumping, the engulfing, the diffusing, it's all done for one reason: to maintain that perfect, stable internal environment that we call homeostasis. It's the delicate balancing act that allows life to exist.
And just to give you a sense of the mind-boggling scale of all this, think about this. Right now, as you're watching this, your body has about 3 trillion of those sodium-potassium pumps firing away. Not per day, not per minute, per second. The amount of work happening inside you right now is just staggering. And that brings us to one last really important question. This whole system of gates and pumps and vesicles works with incredible precision, trillions of times a second. So what happens when those gates start to fail? What does that mean for our health? It's definitely something to think about.